All right, this is our last day of volume by revolution, and then we get to move on to another topic. But volume by revolution is definitely one of the ones that's a little bit trickier, just because it has so much visual reasoning with it. So today we're going to practice a little bit more of you guys doing problems and then just kind of checking back in with me after you've done them. So pausing your video and unpausing it a lot. I want you guys really practicing and pushing yourselves to see if you understand it on your own. So this is from a previously released AP test. It's number 23, which means it's in the non-calculator section. It's also multiple choice. It says if the region enclosed by the y-axis, the line x equals 2, and the curve y equals the square root of x is revolved around the y-axis, the volume of the solid generated is blank. So do me a favor, put your video on pause, do the best that you can to attempt this problem on your own, and then come back together with me once you're done and check your work. So I'm going to pick up right here, just to show you what I've done so far. I drew my shape. Notice that we've talked about this function before, y equals the square root of x, but this time it's a different area it's revolving. So typically in the last one we were working with, they wanted to revolve the area that was underneath that curve, in between that curve and the x-axis. But in this case, they want the region enclosed by the y-axis and the line y equals 2, and the line y equals the square root of x. So it's this little region that's up here. And they want it revolved around the y-axis, so I reflected it across the y-axis. Notice that it touches at every point, so it's only going to have an outside radius, not an inside. This is a vertical line, so everything needs to be in terms of y when I'm integrating, so I had to change this equation from y equals the square root of x to x equals y squared. And then I came over here and I said, okay, my outside radius is top minus bottom, that's y squared minus 0, which is just y squared. My limits of integration are from 0 to 2, because those are y values, from 0 the lowest to 2 the highest. And then it's pi times that integral quantity squared. Now this one, because it's a non-calculator, we actually do need to calculate this by hand. So I just wanted to pick up here, even though I'm pretty sure you know how to do the integral, I just wanted to make sure we were all on the same page as to how to do it by hand. The integral of y to the 4th dy, since y is the important variable, would be y to the 5th over 5. And we're evaluating from 0 to 2, and we have that pi in front. If I use the fundamental theorem of calculus, that's pi times y to the 5th, which would be 2 being plugged in, would be 2 to the 5th. So that's 32 over 5. Minus, if I plug in 0, that's 0 over 5. So this is just 32 pi over 5, which is answer choice A. Next problem. This is a non-calculator question, but it is a previously released AP question. It says, what is the area of region R? So notice that they were kind enough to draw it for us. It says R is the region in the first quadrant that's enclosed by the graph of y equals 2x, which is this straight line, y equals x squared, which is this curved line, and it's shown in the figure above. So this is going all the way back to just finding area. We don't want to find volume. Now, I'll do this one with you guys just because it's been a few days since we've talked about area, and I want to make sure you don't do too much because this is just basic. Area is just this region right here that I've highlighted. I don't need to revolve it around anything. I'm not doing anything like that. I just want to find the area of this region. So remember, to find the area, it's going to be nothing about pi's because there's no circles in this case since we're not revolving it around anything. It's just simply the integral from left to right, so from 0 to 2, of top function minus bottom function. So the top function here is the straight line y equals 2x, and the bottom function is the curved line y equals x squared. So top minus bottom is going to be 2x minus x squared dx. Now notice, again, there's no extra bells and whistles on it. There's no pi in front because it's not a circle. We're not squaring it because we don't need that pi r squared. This is just top minus bottom to represent the height of one of these little rectangles. And the integral from 0 to 2 will add together all of the heights together to find the area of this shape. And this is a non-calculator question, so we have to do this by hand. The integral of 2x is 2x squared over 2, which simplifies to x squared. The integral of x squared is x cubed over 3. And I'm evaluating that from 0 to 2. If I plug in 2, I get 2 squared, which is 4, minus 2 cubed over 3. 2 cubed is 8, so that's 8/3. And then if I plug in 0, I just get 0 minus 0. I'm actually not going to simplify that because this is a free response section, and free response says you can leave it however you want. And I can guarantee you, if I asked some of you guys to simplify that by hand, somebody would make a mistake. So do not simplify your answers. You can't leave it like this because this doesn't show the reader that you know what to do with the 0 and the 2 with the fundamental theorem of calculus, but you can leave it like this because they would know that that's your final answer. If you wanted to put like a -0 afterwards, you can even put a -0 just to show that you knew that the 0 being plugged in gives you 0. But this is good enough for an answer. All right, same problem, but this time they want to know what is the volume when the region is rotated about the x-axis. So I'm going to put my video on pause. Why don't you guys go ahead and put your video on pause and try this problem on your own, and then come back later to check your work. All right, so here's what I got. I reordered the way that the picture looked, by the way, so I could have some room to draw this over here. So I wanted to draw the reflection across the x-axis to show how this region was reflected over the x-axis and then rotated. Trying to think of what this kind of looks like. On the outside, it looks kind of like a cone. So it comes to a point down here, and then it has these straight sides. So it has this conical shape on the outside. And then on the inside, it has like this funnel shape that's being taken out of it. So the circle on the outside, this red one, is the radius is represented by top function minus bottom function. So top is 2x, bottom is 0. And then for the green one, the top function is x squared, and the bottom is 0. Notice that this is a calculator OK question, so I just defined capital R to be 2x and lowercase r to be x squared, and then plugged them into the volume formula. So pi times the integral from 0 to 2, those are my limits in terms of x, 0 to 2. R squared minus little r squared. And then when I put that in my calculator, I got 13.404. All right, next problem. Same region one more time. The only difference is that now we are rotating around the line x equals 2. So I'll go ahead and put my video on pause again and show the work for this problem. Why don't you guys do the same and come back to check when you have an answer. All right, here's my answer for this one. Notice that it's the same region again, rotated around the line x equals 2. So I reflected the area over to the other side. I drew my outside circle and I drew my inside circle. This is kind of the same shape as the last one, where it's this conical shape on the outside with a funnel being taken out from the inside, but maybe just different dimensions. Notice that we're revolving around a vertical line, so everything needs to be in terms of y. So I had to change my functions to be in terms of y. This straight line was y equals 2x, and I had to change it to x equals y over 2. This curved line was y equals x squared, and I had to change it to x equals the square root of y. And remember, it's the positive only because it's on this side. If it was the other side, then it would be the negative square root of y. So I have my functions in terms of y. When I drew my circles, I looked at top function minus bottom function. So in this case, the top function was 2 for the red one, and the bottom function was the straight line. So I got 2 minus y over 2. For the green one, the top function is 2, the bottom function is the square root of y, so 2 minus the square root of y. And then I wrote down my volume formula. Notice that my limits are in terms of y, from 0 being the bottom number to 4 being the top number. So from 0 to 4 of capital R squared minus little r squared. Now, I didn't want to make a mistake. Like, this is a lot to put in your calculator on the home screen, so I actually went in and made my capital R equal to y1. So I typed that in as y1. I put 2 minus x over 2. And then in y2, I put this function. I put 2 minus the square root of x. And then that way, when I was putting this on my home screen, I just had to put pi times the integral from 0 to 4 of y1 squared minus y2 squared, because I was nervous that I wasn't going to put parentheses in the right place, or I wasn't going to do the fraction right. And it's just a lot to look at if you're going to actually plug these into your calculator that way. So sometimes it's easier just to set more complicated expressions equal to y1 and y2 so that you can guarantee that you're doing it correctly. Especially when you're using your calculator, things can get a little tricky, I guess, in the sense of most of the time we just trust what our calculator says, but if we type one thing wrong, the whole answer is going to be wrong. So be very careful. Try to put in some safety precautions for yourself so that you don't accidentally make mistakes in more complicated expressions like this when it's difficult to read. So I got 8.377 or 8.378. And I believe this is the last two examples, but the same problem, just two different examples about it. It says, let R be the region in the first and second quadrants bound by the graph of that function. And it says it's bound below by the horizontal line y equals 2. So find the area of R. This is a calculator OK question, so take a minute and put this in your calculator. I'm going to pause my video and do it, and then I'll show you a picture of what I see on my screen. Why don't you pause your video and see if you can see the same thing. Alright, so here's what I see in my calculator when I plug this in. So 20 over 1 plus x squared, and it's bound by that and the line y equals 2. So I put this function in as y1 and this function in as y2, and then my limits of integration, or my limits of the window, so the window min and max for the x-axis, I went from -4 to +4, and for the y-axis I went from 0 up to 20 because I wanted to see a nice clear picture of what this looks like. So they essentially want to know what is the area of this region in here. So a couple things I need to do. Number one, remember for area, I don't need to get into all that crazy like pi stuff. I'm not revolving it around anything. I just need the limits of integration, which I still need to calculate. I need to know what this point is, and I need to know what this point is. Those will be my limits of integration. And then I'm going to do top function minus bottom function. So my top function is 20 over 1 plus x squared. And my bottom function is 2. And you guys can see that right here. If I can find the length of one rectangle, that red rectangle, it's the function minus 2. So that's where I got that from. So that's the length of one rectangle. If I put those into my integral and I know my limits of integration, it will add together all the rectangles of that length in this area. So let me go ahead and actually calculate what those points of intersection are. So I'm going to go ahead and calculate these points right now to figure out where I need to be integrating. So I'm going to go on my calculator to second calc, and second calc. I want to find the intersection. That's option 5. First curve, second curve. My guess is that it's about -3. Let's see if that's right. Yep, that was right. -3, and then I think it's symmetrical, so the second one would be at +3. All right, so my points of intersection are 3 and -3, which means my limits of integration are from -3 to +3. And this is a calculator okay question, so go ahead and put that in your calculator and unpause your video when you're ready to check your answer. All right, the answer I got was 37.961 or 37.962. All right, why don't you guys go ahead and try this one? So pause your video and then come back when you're ready to check your work. All right, so I drew a rough sketch of the area. It's being rotated around the x-axis. So here's the x-axis. You can see that I have no idea what this looks like. I guess it kind of looks like maybe a top, like a spinning top. You guys ever seen one of those where you take it and you kind of twist it on the ground and it spins around in circles really fast? So I guess it kind of looks like that, maybe not so pointy at the edges, but in the sense that it kind of goes out wider in the middle and then gets narrower again, and it's like that all the way around. So its widest part is in the middle, and it's kind of the circular. It gets kind of narrow at the bottom, narrow at the bottom. And in the middle, it has this cylindrical shape cut out of it. So it's this spinning top, kind of looks like a red onion maybe with a hole cut through the middle or a cylinder cut out of the middle. I don't know. Anyway, here's this red circle, and so the length of the radius for the red circle is top minus bottom, which is the function, 20 over 1 plus x squared, minus the axis of revolution, which is 0. And then for the inside radius, the green one, it's top minus bottom, which is 2 minus 0. Plug that in our volume formula, pi times the integral from -3 to 3. Since we're revolving around a horizontal line, everything is in terms of x, of capital R squared minus little r squared dx, and I got 1,871.190 as my volume. All right, that was the last one for today. So we are going to move on to a new lesson in our next video, and we are getting near the end.